Hello students, today we are going to learn about the kinetic energy in pure rolling. First, what is pure rolling? Consider one object. Okay, so this is the one disc. That disc is a circular object. Okay, that circular object is moving. So it contains two motion. What are that motion? Translational motion and rotational motion. Okay, there are two motions are acting in that rolling. Okay, what are that? Translational motion and rotational motion. Okay, then kinetic energy in pure rolling. So kinetic energy, we are going to calculate that kinetic energy. So rolling means that is the combination of two. One is the translational and another one is the rotational. So we want to calculate that kinetic energy. So kinetic energy is equal to, here two motions are there. So we want to sum up the two kinetic energy. Rotational kinetic energy and translational kinetic energy. Okay, rotational kinetic energy in rotational plus kinetic energy in translational. Okay, so we are calculate the two kinetic energy, rotational kinetic energy and translational kinetic energy. You can sum up these two kinetic energy, we can get the total kinetic energy in pure rolling. Okay, do you understand? So pure rolling means there is the combination of rotational and the translational. So kinetic energy means you want to calculate the total kinetic energy is equal to sum of rotational kinetic energy plus some translational kinetic energy. Okay, so what is kinetic energy? Kinetic energy is the energy possessed by a virtue of its motion is called as a kinetic energy. If an object is in motion, it having some energy, that energy is called as a kinetic energy. So here translational kinetic energy is acting on that rolling body and rotational kinetic energy is also acting in a rolling body. So you can sum up these two kinetic energy, we can get the total kinetic energy of pure rolling. Okay, now kinetic in translational motion. Consider one object. Suppose that object is moving in a translation. Translation means it is moving in a straight line. Okay, so it having that mass m and velocity v. What is that kinetic energy? In translational motion, that kinetic energy is equal to of mv square. Okay, suppose if the object is moving in a rotational path. Okay, so this is the starting point. That object is moving in a rotational path like this. Okay, so what is that kinetic energy formula? What is the kinetic energy formula? Of I omega square. We already discussed. Okay, so kinetic energy in rotational is equal to of I omega square. Here m is the mass of an object. Here I is the moment of inertia. That moment of inertia represents the mass of an circular object. Okay, here v is the velocity, linear velocity of an object. Omega is the angular velocity of an object. Okay, so here translational motion. So translational motion, we have that mass m and velocity v. Okay, but in rotational motion, that mass is I and angular velocity is omega. Okay, now these two values you can substitute here. This is the first equation and this one second equation and this one third equation. You can substitute third 2 in 1. So we can get kinetic energy is equal to kinetic energy in rotational. What is that formula? Of I omega square plus of mv square. Okay, now that object, so here rolling object, that rolling object only depends upon that center of mass. Okay, if that object is moving in a translational motion, that will be depends upon that center of mass, and if the object is moving in a circular rotational motion, it also depends upon the center of mass. So I put a center of mass ICM, here VCM. Okay, ICM is the center of moment of inertia in a center of mass, and VCM is the velocity of center of mass. Okay, so this is the equation number 4. Next, we are going to calculate that with center of mass as a reference. Okay, center of mass as a reference. Mass as reference. Okay. So what is the formula? Kinetic energy is equal to ICM omega squared plus half m v squared cm. Okay. Already you know that the general equation for moment of inertia. What is that? mk square. Okay. Then here that object is in a rolling motion. Okay. So rolling motion means we have the angular velocity. So what is the relation between linear velocity and angular velocity? V is equal to r omega. So this is the relation between linear velocity and angular velocity. V is the linear velocity, omega is the angular velocity. V is equal to r omega. Then VCM is equal to r omega. Then omega is equal to VCM by r. Okay. So this is the equation number 5 and this is the equation number 6. Okay. So you can substitute 5, 6 in 4. We can get kinetic energy is equal to half ICM omega square. ICM you can substitute mk square. Then half mk square omega square. Half mk square omega square plus half v squared cm. Half v squared cm. V squared half mk square omega square. Now you can substitute VCM by R. So omega is equal to VCM by R. Then omega square is equal to VCM squared by R square plus half VCM square. Okay. So in this case, so what are the terms are common? Half is common. Okay. So kinetic energy is equal to half is common and m. Here that m is also common. M and VCM square. This is also a common. So V squared Cm and remaining term. What are the remaining term? Here k squared is there. K squared by r squared. Here 1. So 1 plus k squared by r squared. Whatever may be. K squared by r squared plus 1 or 1 plus k squared by r squared. So both are equal only. So total kinetic energy in pure rolling is of m v squared cm of 1 plus k squared by r squared. Okay, do you understand? So this is the with the center of mass as a reference. Then next with the point of contact as a reference. Next we are going to calculate at the point of mass as a reference. With point of contact as a reference. Point of contact as a reference. Okay. Then now that object is moving, so that object is contact with this point. Okay, only one point is contact. So in this point, what is that kinetic energy? So it is considered as a rolling motion. Considered as a rotational motion, not in a translation. Here the point of contact as a reference, we are taking in a momentary, taking in a rotational motion alone. Okay. So rotational motion, kinetic energy is equal to, in rotational motion, what is the formula for kinetic energy? Of I naught omega square. Okay, of I naught omega square. Now, according to parallel axis theorem, what is that mass? So here, this is the point of contact, another one axis is there. So this is the distance R, capital R. Okay, and mass is capital M. So what is the total moment of inertia? I naught is equal to, according to parallel axis theorem, I naught is equal to I Cm, that is center of mass of moment of inertia. So this is the one axis is passing through its center of mass. So that moment of inertia plus, that is sum of or plus product of mass and square of the distance. So mass and square of the distance. I naught equal to ICM plus MR square. Already we discussed the parallel axis theorem. Okay, you can then here ICM means the general equation. What is that general equation for moment of inertia? ICM is equal to mk squared. So mk squared you can substitute here. Then I naught is equal to mk squared plus mr squared. Okay, you can substitute here. And also here omega you can replace by omega is equal to VCM by R. Then omega squared is equal to V squared Cm by R. Okay, you can substitute. Then kinetic energy is equal to of I naught. You can substitute mk squared plus mr squared into I naught. Below you can substitute mk squared plus mr squared and remaining omega squared. So omega squared is equal to V squared Cm by R squared. Okay, V squared Cm by R squared. In this term, which one is common term? You can take them out. So of m is common and V squared Cm is common, and V squared and Cm. Okay, and remaining term mk squared. So m is commonly you can take them out. So k squared. So you can multiply with the divide it with the r squared. So k squared by r squared plus then r squared divided by r squared. That value is 1. Okay. Or the kinetic energy is equal to of m v squared Cm of 1 plus k squared by r squared. So you can compare these two equations. So this equation and this equation. So both are same only. So this is the with the center of mass as a reference, but this is the momentary taking in a rolling. Okay, sorry, momentary taking in a rotational motion. So both the kinetic energy are same only. Suppose if you are solving the kinetic energy in pure rolling problem, you can consider any one cases. Okay, so if you consider with the center of mass as a reference, that is the combination of rotational and translational motion with the center of mass. Okay, or with the momentary contact in a rotational motion. Okay, thank you.